Hey guys, welcome back with Mrs. Stribble. So today we're going to talk about comparing populations and random samples. We've been going through our statistics chapter and discussing how we can use measures of center, measures of variation, and even random samples to predict different things about populations. Now we're going to use those in order to compare populations. So I had asked you for this to go ahead and take a look in your book for some questions concerning our notes. Okay. So here, our first section, comparing populations. Notice at the top, it gives us some very important information. When we are comparing populations using measures of center and variation, we're going to use the mean or the average and the mean absolute deviation when the two populations we're comparing are symmetric to each other. So they're very similar to one another. They're neatly laid out as far as the length of each whisker or the distribution of the data is symmetric. Okay. We're going to use the median and the interquartile range when either one or both populations' data is skewed. Okay. To find more information on symmetric or skewed data, please make sure to see my video containing box plots and how to interpret those and make those. That is also in there. That information is also in there. Okay, so obviously this top information is very important information. We need to know when to utilize each measure of center or measure of variation. Okay. So when we are taking our notes here, we would say that when the data is symmetric, oops, maybe, been going slow on me here. Okay. We are going to use the mean to compare the measures of center. And we're going to use the MAD to compare the population's variation. Okay. So we're taking two different types, or at least two different populations, and when that data is symmetric, we'll use the mean to compare their measures of center and the MAD to compare their measures of variation. When the data is skewed, whether it be one of the populations or both of the populations. So when that data is skewed, it doesn't matter, it can be skewed to the left or skewed to the right, but it's skewed some way. Okay. When that happens, we need to use the median to compare the measures of center and we're going to use the IQR or the interquartile range to compare the variations between those two populations. Okay, all right, so there's that important information we better make sure we have down in our notes. Let's head back on here. Okay. Another thing we might want to do is literally write out this example. So we have two data sets, and it's a double box and whisker plot. This is where box and whisker plots are most used, actually, is to compare populations. So whether I'm talking about how long it takes girls on average to go to work and boys on average, those are two different populations, and we're comparing them. So the first thing we need to do is compare the data set. In order to do that, we need to figure out, is it symmetric or is it skewed? And taking a look at this data, we notice that the red data, or data set B here, is definitely skewed, okay? And more on that, data set A is also skewed, slightly less than data set B, but they're still both kind of skewed. If you take a look at the whiskers, that's your dead giveaway on box plots. The one's fairly larger or longer than the other. That means your data is skewed. Okay, so our data is skewed here. We're going to use the median and the interquartile range to compare the data sets. The median on a box plot is super easy, right here. So we have 60 versus 90. Okay, and then our interquartile range, because they're skewed, would be 80 minus 30, so 50 here, and then only 20 here. There's our medians, there's our interquartile ranges. And now we're going to compare them from one population to the next. So we would say that data set B has a higher median by 30 units or points or whatever we're talking about. And then we would say that data set A has a greater interquartile range than data set B. So it's more distributed, it's more spread out.
So dataset B has a greater measure of center, and dataset A has a greater measure of variation.
Exactly.
Part B. Which dataset is more likely to contain a value of 95?
Okay, so value of 95, we got to look at which, we have to look at our box plots here, and which section of the box plot 95 is contained in.
Remember, in a box and whisker plot, about 1/4 of the data are in each whisker, and about 1/2 of the data are in the box. So, about 25% of the data values in dataset A are between 80 and 130. About 50% of the data values in dataset B are between 80 and 100. So, dataset B is more likely to contain a value of 95.
Okay, another way to think of it is this way. So here's 95, and it's within 5 points of 25% of the data in dataset B. Okay, so it's fairly close. We have only 10 numbers in between here that represents 25% of our data. Whereas here, 90 to 100, we don't necessarily know how many points are there. All we know is from 80 to 130 is 25% of our data. We have a better chance here. We have more percentage in data set A within this range, in this section of the box plot. So that's another way to look at it. And C, which data set is more likely to contain a value that differs from the center by at least 30? So let's take a look at the centers. Here's 60. 30 away from 60 on both sides is 30 and 90. Okay, so we have 25% of the data on this side, and probably slightly less than 25% of the data here. Okay, so that's data set A. Data set B, if we take a look at 30 points away from the center, we don't have anything greater than 30 points away. But if we take a look lower, We have maybe 20, maybe shy of 25, okay? So we can see that data set A is definitely more distributed and will have a more likelihood of containing a value that's 30 points away from the center here, okay? It's got this whole section that's 30 points away, which is 25% of the data, plus most of this section, whereas this one only has part of a 25 percentage.
The interquartile range of dataset A is 50, and the interquartile range of dataset B is 20. This means it is more common for a value to differ from the center by 30 in dataset A than in dataset B. So, dataset A is more likely to contain a value that differs from the center by at least 30.
Okay? Oops. All right. Now we would go to the next one. You would do these try-its. Hopefully you've done that. I'll check back later on that. Okay, this second example at the top, always read that top. When two populations have similar variabilities, the visual overlap of the data can be described by writing the difference between the measures of center as a multiple of the measure of variation. Greater values indicate less visual overlap. So here's kind of what that means. If I have some data and gosh, these are not very different from each other as far as how they are distributed. So we've got 90 minus 20, that's 70, and then we've got 60 minus 10, that's a range of 60. Okay, so they're fairly close in the distribution or the variability from one population to the next. Then now we can look at the visual overlap. From right here is what we call the visual overlap. Okay, and we can describe this by taking the average or the mean of both data sets and then placing that as a multiple of our MAD, which is going to be our measure of variation here. So we would take the difference between the means, the difference between the averages, and we would divide it by the mean absolute deviation. Okay? And what that tells us is how much visual overlap there is. Okay, and we're looking for small numbers. Again, here, the greater the number, that means that there's not much overlap. So we're looking for smaller values here to describe populations that overlap quite a bit. Okay, if you got a large number as your answer here, then you might want to double check some values because we should get a small number here. So let's go ahead and play this and see what number we come up with for the difference in the measure of center as a multiple of the measure of variation.
The mean is equal to the sum of the data, 810, divided by the number of data values, 15.
So I want to run something by us real quick. Where they get the 210 for data set A. When we have dot plots or when we're comparing any populations using any data display, we put the data on the same number line. Okay, so if you notice this number line is the only one with values on it, that's because these number lines mimic each other. So where there's 20 here, this would also be 20. Okay, so we would have 20, 30, 30, 40, 40, 350s, 360s, so on and so forth.
To find the mean absolute deviation, first find the distance between each data value and the mean. Then find the sum of the distances. The mean absolute deviation...
And we discussed how to find the MAD in class. You can also look it up.
36 divided by the number of data values, 15, which is approximately equal to 16. Now, to express the difference in the means as a multiple of the mean absolute deviation, divide the difference in the means by the mean absolute.
Okay, so this is where we're doing what we're doing. We calculated the means, we found that the MADs were equal to each other. So now we're going to find the difference of the means and divide it by that MAD of 16 in order to see how much overlap there is. Again, we're looking for a small number here.
Absolute deviation. The difference in the means is 26, and the mean absolute deviation is 16. 26 divided by 16 is approximately equal to 1 6/10. So, the difference in the means is about 1 6/10 times the mean absolute deviation.
Okay, so yep, there's that small number. That tells us there's quite a bit overlap in this data. Right? And then you would do the triads again. That's comparing populations. Now we could also use random samples to compare populations. Let's go ahead and talk about those. And I'm going to try and move things along a little faster here for this section, okay? So it says you do not need to have all of the data from two populations to make comparisons. That's where our random sampling comes in, okay? So we can also use these random samples. So we have random sample A and random sample B. We can use these two random samples, okay, and do the exact same that we did in the previous section. Calculate each measure of center, compare them, and then calculate each measure of variation and compare them. Taking a look at this data, though, we see that this one, bag A, it seems skewed. It seems slightly skewed here, okay? So we're going to have to use the median and the IQR in order to represent the measure of variation and center. All right, so I'm going to do the click through. It seems to be just quicker doing that way. For bag A, 4, and then the IQR would be the 6 minus 3, so that would be 3. Bag B, the median is 3, and then we have the IQR of 5 minus 2, which is 3 as well. Okay, so here, the median of bag A is slightly larger than bag B, but the IQRs are the same. We conclude that tiles in bag A generally have greater numbers. Not really. We'd need more of a sample, okay? And then we could conclude that. You're more likely to make valid comparisons when the sample size is large, okay? We need that variability. We need those large samples. All right. Then try it. And then again, just like we did before, we don't have to have the entire population. We can use random samples and determine different things about here. So it says the box and whisker plot represents the medians of 50 random samples out of 12 numbers from each bag in sample 1 compared to the variability of sample medians in the variability of the samples in example 1. Can you determine which bag contains tiles with greater numbers? Go to the click through here. Can we determine which bag contains tiles with greater numbers? 75% of the tiles we picked, and that would be 9, sorry. That would be 9 tiles are actually greater than any of the tiles picked in bag B. So we can assume that we can assume that bag A contains greater numbers, for sure. Okay. Yes, it's a small sample size, but there's big enough difference that we can definitely make a safe assumption here. All right. And then you go ahead and do the try it. And that pretty much covers it. So going back here, sorry. All right. Thanks for joining me. And I'll see you guys next time.